Okay, so we're back. So we had just, in the first part, we had just figured out what the quantitative shape was, and now we're going to try to get around to figuring out the actual values. Now, remember we have this neat thing about shear, is that these changes in shear we always know are 1. So I've got 2 of them. So that's going to be 1, and that's going to be 1. And I'm done. This is 10 feet. This is 10 feet. This is 15 feet to the end. So that's it. So very similar to the first part of the problem, we'll start with the dead uniform load. And what do I have to do? Well, remember my dead load is 0.4 kips per foot. I just have to multiply it by these 2 areas. And if you'll notice, there are 2 triangles. They're the same, right? They both have the same base of 10. They both have the same height of 1. So I'm going to start off with my 0.4 kips per foot. That's the actual dead load. And I'm going to have 2 triangles. And each triangle is 1/2 the base, 10 feet, times the height, 1. So these 2's cancel. I got 10 times 0.4 is just 4. And then my live uniform load. Now this one I can move around again, but in this particular case there's not much to move around. I'm going to run it from 0 to 10 to cover this positive section, and then from 10 to 20 to cover that positive section. And that's it. Again, I have 2 of those, so I've got my intensity of 2 kips per foot. And again, there are 2 of those areas, and each one of the areas is 1/2 base times height. So it looks like I get 20 kips for that. And then finally, I have my live point load, which can move around. And really, there's 2 positions it could be in. It could either be here, right, at the very far end. That's where it has a value of 1. Or it could be just to the right of A, where it also has a value of 1. Either way. So it doesn't really matter which one. You can't have both. You pick one. But either way, they both have an ordinate value of 1. So it would still be 8 kips times 1. And that would give me 8 kips. So the maximum shear at A, just to the right of A, is going to be 24 plus 8 is 32. And if we look at how that's located, here's my pin and my roller. So just like in the previous problem, my uniform dead load is going to go over the whole structure. And that's going to contribute 4 kips to the shear. I did forget to tell you that this is A and B and C. And then the live part, I'm going to locate that over the 10 feet and the 10 feet. So that'll be over this portion. And then finally, my live load. And it could be 2 places. One is right over the support, or one is over here on the far end. I'll put this one right over the support. No particular reason. Actually, I could do it this way. I could say this or that. Either one. They're equal. That would be, this position would be here, and the second position would be just over the support. Actually, just to the right. If you look at what we did previously, I think those are, interestingly, very close to the same. But remember, the reaction at A and the shear at A, just to the right, they're pretty closely related. So let's finish this problem by doing the part C, which is the maximum negative moment at C. I think we'll find there it'll be a little bit different. So I'll cover that part up. We'll have the beginning of the so we need to redraw the influence line for the moment at, what did I say? Forgot now. C. So here's my structure. So let's see what it looks like. I've got to this pin. This is a roller. Now I'm going to come to C and I'm going to remove its ability to withstand moment. So it's a fixed connection. And if you take the moment away, really what you have is a pin. Right? And then what am I going to apply to it? Positive moment. So how's that going to move? How is this edge going to move? Is it going to rotate up or down? It's going to rotate down, right? And then hinge, and then seesaw over the supports. Looks something like that. So there's my qualitative shape. And it's driven by the fact that this moment is trying to take this edge and rotate it counterclockwise. So now if I draw my influence line for the moment at C, let's get all the bits and pieces there that I need. So I know what it's going to look like. I just need to find some values. I know this is 10, this is 10, this is 15. Yeah.
Back to the question asked for maximum negative moment. When you apply your moment, you apply positive moment.
Always apply positive moment.
Always do. And it comes out positive.
Comes out positive, it's positive. Comes out negative, it's negative. What was I going to say? Oh, yeah. So we now have to find the moment at C, which is really this reaction moment over here. And what position do you want to find? Well, probably this is going to be a good point to find. That's right at this point, which is right above B. Or all the way out here, which will be the load there. So we want to find the reaction at C with our point load here or here. I think B is going to be the easier of the two, right? Because if you imagine your structure, and I'll do it here, I'll separate it. We're going to have to take it apart here at B. So I'm going to have a reaction at A. That's a pin, so I've got one part, reaction at A. I'm going to take it apart here at the pin, so I would have a shear at B on this side, and of course equal and opposite a shear at B on that side. And then my structure would roll on into C, where I would have a shear at C and a moment at C. And that's what I'm trying to find, the moment at C. So again, if I want this value, my unit load would be right there. If I want this value, my unit load would be right there. You guys see the difference? I like this position. And why? Well, I don't have to worry about any of this stuff. There is no load there. So what's the shear at B when there's no load? 0. So I already know that my shear at Z in this particular case is going to be 0, which means the shear at B here is also 0. So all I have to find is the moment at C for a unit load 15 feet away. This was 10 and 10. So if you come here and you say, hey, I'm going to sum moments at C, make sure it's in equilibrium, well, what do I have? Well, I have the moment at C, which is positive. The The shear at C creates no moment at C, but my point load does. And it creates a positive moment with a moment of force of 1 and a distance of 15. So my moment at C is going to be minus 15 feet. So that means this value right here is minus 15 feet. And similar triangles tells me that if this is 10 and this is 15, then what should this height be? Also 15. So there's my moment at C influence line. And now I can just apply what I did before. So I'll start with my dead load. And remember, the dead load's applied to the whole structure. So my dead load was 0.4 kips per foot. And now you can see that I've got a positive area and a negative area. I'm just going to have to add them up. They're both triangles, so they'll both have a factor of 1/2 in front. And now I'll sum their base and height. So starting here, I've got a base on my positive triangle of 10 and a height of 15. On this triangle here, I have a base of 25 feet and a height of minus 15 feet. So what's that? 15 times 15 is what? What's 15 times 15? 225. Half of that is 112.5 times 0.4. I don't know. You guys have to tell me what it is. That's not one I can do my numeral magic in my head.
Can you explain how you got the numbers in the brackets again?
Here, let me do it this way. So if you look at this area right here, what's the area of that triangle? It's 1/2 base times height. You see that? So then you look at this triangle. What's the area of that? Well, it's the same 1/2, and there's the base, and there's the height. The height here just happens to be negative. That's how I took care of the negative part. Anybody get that number?
Yeah, 45.
45? Anybody else get 45? Sorry?
It's negative. Yeah, it's negative.
Negative 45?
Yeah,
that makes sense. So that'll be 45, and this is going to be kip feet. So let's do the live load. Uniform load. Now what changes here is this problem wants the maximum negative moment. So I put the live load over the part of the beam that creates the best negative area. And what's the best negative area? Should it be over 0 to 10? No, that's positive. So it's got to go from 10 to 35. So that area times the intensity of that load, so it's going to be 2 kips per foot is the load. It's a triangle, so it's 1/2. And what's the base of that triangle? 25. And the height, minus 15. Well, conveniently, those two cancel, so you get 25 times 15, which is 375.
Yeah.
That's negative 375, and that'll be kip feet. So then finally we get the live point load. So where should it be to create the maximum negative moment? Well, find the maximum negative value on the curve, and it is negative 15. So that'll be 8 kips times negative 15 feet. That's that 120? Negative. So now we have to add all those together. So the maximum moment at C is going to be all that. So that's 420, 40, 540. Is that right?
Yes.
Oh, forgot my minus sign. Negative. So what does that look like? So I'll redraw the beam here. Don't think I have it to scale, but I think you'll get the idea. So there's the original beam. If I start with the dead load, well, it goes over the whole structure. So there's the dead load. Then I'll go to the live load. Now, where did I put the live load? I just put it from here, which is right over A, to the far right of the beam. So that goes here. So there's the live load. And then where do I put my point load? Right there, which is right over B, which is right here. So that configuration of loads, 2 of them live, 1 of them dead, produces the maximum moment at C, which is the reaction. So any questions about that? I guess you had some to start with. Hopefully that cleared it up or helped.